Okay, now we step up to the nice computer, and we're going to see if it works. Here's something fun. When you're upgrading your software, which, by the way, I did the other day, and you know why I did this, and it's important. See this? That's right. It's the iPhone 4S. Anybody else have one? Oh, no. When you're a roller like me, dude, no problem. 4S, I did that, and I decided, hey, this is great. I'll update my computer. And in my joy, I forgot a fundamental rule. And by the way, this rule will seem awkward to you, perhaps, but the rule is you don't upgrade your computer. Why would you do that? And here's why you don't do it. You don't do it because when you upgrade your software, all of a sudden, inevitably, some piece of software won't work. So in my joy, when I was going like, hey, what's up, I wasn't talking to anybody. Because I don't really talk to anybody on the phone, except for my mom, but I didn't want to talk to my mom. So I said, do you want to upgrade? Say, yeah. Party. And then what doesn't work? MATLAB. I would swear in class if I wasn't on tape. But this is the kind of thing that happens. But however, MATLAB still works in what's called no JVM, no Java Manager mode. So you can still launch it, do everything you want. It's just that it's a little, it's whatever. It still works. But anyway, I still have a iPhone 4S. That's maybe the ultimate take-home story of the whole thing. And let's program. Okay, here we go. I got the basic commands up here. Can you guys all see that all right? Clear all, close all, do everything. So let's start thinking about what we need to do our program. So first of all, let's figure out how long a time we're going to solve this for. Let's do something simple. Actually, do 1 to 10. Okay. So my time span will be 0, steps of 1 to 10. Remember, very important, don't say 0 and 10. Okay? If you do that, you're going to get massive amounts of data back because it's going to give you all the information at every DT. And the DT here might be 10 to minus 3. So it'll give you 1,000 pieces of information. How big is this information? Like if you discretize in 100 by 100 points, it's huge. Right? So it's 10,000, a matrix of that size, of 10,000 components. And it will write it out 1,000 times per 1 unit of time, which means 100,000 times, right, if you're going to go out to 10. So anyway, it's a disaster for you if you decide to do that. So pick out your times that you want. 0, 1, 10, good enough. All right? Now we have some parameters in the problem. There's one parameter, mu, there. And we'll make it small. I think we have it 0.001 in the code. And now we start breaking things up. Now I'm going to make the code even simpler than in the notes. We're going to break this up into a square. We're going to say something like L will be 20. So in other words, it's going to go from negative 10 to 10 in the x direction and negative 10 to 10 in the y direction. We'll just make it symmetric like that. Fairly simple. A box that we're going to solve on. And so you say, okay, I got that L. And now what I got to decide to do is how do I want to chop it up? How about 100 points? In fact, let's start smaller, 64. We're using FFT, so we'll do a power of 2. So 64 is a power of 2. Okay? Remember what the FFT is going to do. It's going to take this problem that's 64, size 64, break it into 2 problems of size 32, 4 problems of size 16, 8 problems of size, I'll let you do the math. All right? And then we just say, well, x2 is a linear space that goes from negative L over 2 to L over 2 in n plus 1 points. But the points I really want are just the first 1 through n components. Remember, it's periodic boundaries. The last point is the first point. So when I do this n plus 1 points here, the n plus first point, which is the end point, is really the first point. I'm not going to keep it around in my solution because I'm recomputing it. So I just take the first 1 through n points. Okay, fairly standard so far. Now, what about the y direction? Well, the y vector is going to look pretty much the same, right? It's going to go now, but it's the y direction. It's going to be negative 20, negative 10 to 10, breaking it up to 64 points. So I could just do the following. Y equals x. Same vector. At this point, x and y have no conception about that there's an x direction and a y direction. It's kind of like when I asked the phone the other day, my Siri. I was playing around with Siri. You know, she's on here, this girl that's supposed to answer all my questions. And I asked her, hey, you know, remind me up to call somebody when I get home. I was just testing it out. And she responds by saying, I don't even know who you are. Can you believe that? That's what she said. How do you know anything about you? It's like, I own you. How do you know that I know about me? She said, just point me out in your mailbox, like in your contact list. Who are you? And then I'll know. So I did. At this point, it's kind of like this code is asking the same question. I have no concept of what x direction and y direction means, so you better tell me what it is. And so that's how you do this with the mesh grid command. Doesn't know who I am. I held her over the toilet for a bit. Oh, yeah? You don't know who me now, huh? Huh? You want to go for a little swim? Okay. Anyway, that's just mean. All right. Everybody good with that? Mesh grid, x, y. And now it's going to create two matrices. Capital X, capital Y. There they are. And what these now are matrices that have directionality. X direction, Y direction. By the way, mesh grid can be used in a higher dimensional way. So if you want to do a three-dimensional cube of data, like you want to represent something in 3D, you would do mesh grid X, Y, Z, X, Y, Z. And then it makes a cube of data, and so you can represent something in 3 dimensions. By the way, 3 dimensions is fine. We can visualize it, but really you can go to 4, 5, 6. Big deal. Instead of a cube of data, you have a hypercube, right? You have components in a matrix of the J, K, M, L components, right? You can't visualize it so easy because it's 4-dimensional, but it doesn't care. Mesh grid doesn't care, okay? So if you want to represent data, mesh grid tells it directionality. Okay, so this is what we've got. We've got this mesh grid. We've got this. We've got things defined. Let's go ahead and make up some initial data that we want to maybe plot. And we've been playing around with vorticity. So the initial vorticity might look something like this. I'm going to make up a vortex here. This is going to be a Gaussian that we'll look at it in a minute. So here it is. It's a Gaussian, and I've given different. So it's really an elliptical Gaussian-looking thing, right? So I've given it different x and y direction, and so we can do the following: p color x, y, w. And so if I run this, file, save. See, now I have to do that, and I don't have a run button there. I know, sad. I held my, well, okay. I don't want to say I held my laptop over the toilet, but I thought about it. But it really wasn't the laptop's fault. It was my fault for saying yes. All right. There you go. There is my initial vorticity. A little ellipse of vorticity. And we can even stretch it more. Let's make 2 times or something like this. And then let's make also shading interp, which makes it look a little nicer. File, save. I guess I could do Control-S. That's fine. All right, there we go. There's our little vortex. Okay? And our question is, what happens to that vortex when we start doing this to it?